this is a schedule for our second half. We have only 11 lectures left from now on, including today's lecture, and this is the timetable for our remaining lectures. So we are here today, so lecture 14, and I guess that this is a holiday due to certain substitution one, and I guess that this is official week for final examination, but unfortunately I have a business trip to Hawaii, so instead of this official week reserved for final examination, this will be the date for our final examination. So Wednesday, just the usual normal lecture day. So I am afraid that I cannot give you enough time, like 19 minutes for the final examination. So if all of you guys are agreeing, then maybe we can start a little bit earlier. For example, 15 minutes earlier than usual lecture time, and we may start 8:45 to 10:15 to secure 90 minutes long lecture or examination. So of course that really depends on your agreement. So this is not the time to make the final decision. So but later I will ask you once again whether all of you guys can come 15 minutes earlier to the lecture room to secure 90 minutes long final examination. And another one is here we have a lecture 19 on Monday, May 18th, but I have another schedule in Seoul, so I have to make recorded video. I will upload on recorded video to my YouTube channel, so just to watch it, so that it will be enough for our lecture 19. Okay, so when we consider our lecture contents, actually we are more than halfway in the lecture progress. The first one was understanding the behavior of a MOS capacitor. We've done, and we are now almost finishing our long channel analysis. So today and maybe the next lecture will be devoted to the wrapping up the discussion about long channel MOSFET. So maybe that will be the end of our part 2, and the remaining lectures, like about 9 lectures, will be devoted to the final one about short channel MOSFET. So short channel MOSFET will be the main topic of this lecture, and actually short channel MOSFET is the MOSFET. Actually there is no long channel MOSFET in these days, so we will just study very important topic. So from my previous experience, maybe this one there can be significant delay in the lecture progress because the content is a little bit more difficult than the one we have seen up to now. So please let me accelerate the lecture progress. We have tons of things to be discussed in this lecture. I wanted to teach you more and more stuff because that is practically very important. But if I have to spend too much time on specific solution procedure, for example, Poisson equation in a two-dimensional box, then that will significantly delay our lecture progress. So please let me skip the detailed solution procedure. So it means that just attending this lecture room is not enough for your study. So you have to do your own derivation for certain formulations. But please allow that kind of additional work from your side, not my side. Okay, so if you don't have any question or comments, then let's go to the very first lecture after midterm examination. So here we have the factor M. Simply speaking, I have prepared many slides, but let me just directly show you the most important one. Please just read the lecture material. Here we have some diagram. So this diagram just shows the capacitive structure of our MOS capacitor or channel or reason. Here we have a gate, yes, and of course this ground means the substrate contact or body contact, and between them we have two different capacitors. One is C-ox, oxide capacitance. You know, this one is physically seen as a very really thin layer of dielectrics. And here we have depletion capacitance, and it is actually corresponding to this layer. Here we have a very thick substrate, and somewhere here we have depletion layer, and here we have neutral layer, and this neutral layer does not contribute any of capacitance to our problem. So that is, although there are certain range, but that is not contributing to our diagram. Only this part is contributing to our capacitance analysis, and this is corresponding to that one. I think that everybody in this room understand this kind of behavior. And point is, the very essential point of our MOS operation is what we can change is only this gate voltage. We cannot directly change the potential at this surface, silicon and silicon dioxide interface. That is defined as phi sub s in our notation, and we wanted to change this phi s. But unfortunately, this phi s is not directly connected to our metal contact. What we can change is only this gate voltage. This is controllable. We can control this one, and we wanted to just change phi sub s. Let's say this one. If we change gate voltage, and let's say our surface potential is exactly changed the same amount. For example, when I increase gate voltage about 0.1 volt, let's say that also surface potential is increased by exactly same amount of that additional gate voltage. Then we will say that gate voltage just perfectly control the surface potential. That is the one we wanted to have. We wanted to have the 100% efficiency of voltage conversion from user-definable gate voltage to the internal surface potential. This is the ideal case. If we wanted to have this kind of behavior, then what does mean is when we increase it by amount of 1.1 volt, and that is also 0.1 volt increase. So that is the situation we wanted to have. However, this M factor here just to specify the ratio between our gate voltage and change of gate voltage and change of surface potential. So since we have here, this is important, since we have here another capacitance here coming from depletion capacitance, that's the reason why, although when we change a certain voltage, this one, the potential at surface does not follow exactly that change. Let me just give you one concrete example. Let's say we have a certain Cox value and happen to be our depletion capacitance is equal to this value. This is just an assumption, so there is no way to have exactly same value, but say that we have the same amount of Cox value here, and let's say we have applied this small change in our gate voltage, then obvious answer is the amount of potential change at this point would be, what is it? It is just half of it. So we will have just reduced amount of change in our surface potential. So that means that we have so although we have changed 0.1 volt, but internally it does not change much, and that is not good for our purpose. So here please note that M factor is defined as just delta V over delta phi, not in delta phi over delta V. So usually this factor is larger than 1. So if that is 1, so they are upper and lower are the same, but in many cases our surface potential does not change as drastically as delta Vg, so we usually have the value higher than 1. However, once again the ideal factor is M quite close to 1, and we wanted to have this kind of behavior. Okay, once again, so at least in this slide you have to understand the factor M is defined as the ratio or relative magnitude between gate voltage change and surface voltage change, and that should be close to 1, and then that is the ideal case. So let me just although I have prepared today, so saturation current 1, but I think that is quite much straightforward, so I will just skip and pinch up also. So now let's go to this substrate current from now on. So here I have prepared quite many slides, but the point is quite straightforward. Here we have total charge, and total charge can be considered as a sum of this depletion contribution, and also this one is inversion or electron contribution. So we have seen this expression previously. And when we consider, for example, strong inversion case, then actually this one will be the dominant factor. However, from now on in this slide, we are now currently considering sub-threshold current. It means that gate voltage is lower than our threshold voltage. Let's say that, for example, let's say that this is happen to be gate voltage is equal to 0.3, then we apply 0.0 or 0.1. We are currently considering this case. Then, of course, if we have this condition, we would say that ID is quite close to 0, because ideally if we apply gate voltage sufficiently lower than threshold voltage, then ideally we have to have vanishing current. And actually that is the truth. We have extremely small amount of current at this substrate case. But point is, once again, whether that is really 0 or whether we have a slightly remaining current, that introduce quite much difference in our chip. Here, let's say this is a top view of a chip, and let's also introduce a certain color map for whether certain part of a chip is running or just sleeping. Then, for example, when we make a snapshot of a certain CPU or GPU, whatever, then in many cases there is a certain heat map like this in an entire chip. Only part of a small part of a certain chip area are actively running, and they are spending the active power here and there. Then obvious question is what happening in this green area which is not actively working. So in this case, the transistors are usually in its sub-threshold region. Gate voltage is equal to 0. So ideally, in this case, current equal to 0, although voltage across this device is corresponding to VDD, since drain current is equal to 0, so the power consumed by this transistor should be 0. This is our argument for power consumption. Power consumption is simply given as the product between voltage and current. Although we have a non-zero, quite high voltage difference, but since the current is exactly 0, so power consumption is 0 in ideal case. Unfortunately, this is a given number, and say that now we have slightly non-zero current, quite small, but not exactly 0. For example, it can be orders of 1 nanoampere, or even smaller, 1 picoampere, let's say. Then, can we say that this is really 0? Say that voltage VDD equal to 1 volt, and we have just 1 nanoamp. Oh, this is quite small. So then what will be the power consumption by this single transistor? Then we will just spend 1 by producing this 1 volt and 1 nanoampere. Then we will have just power consumption by 1 nanowatt. This is quite a small amount of value. But if we have 1 million transistor, then what will happen? If we have 1 million transistor, each of them is spending 1 nanowatt, then the product will be just 1 milliwatt. So simply speaking, what I wanted to say is, in general, we assume that the turned off transistor does not consume any kind of power. But unfortunately, although each of them spend quite a small amount of power, 1 nanowatt or 1 picowatt, or even lower, but since we have a lot of transistors inside our system, the overall product by this idle transistor can be quite high. So are you with me? So please make just a simple argument. Here, power by idle transistors. So how many transistors you have in your system? So what will be the number of transistors right now you have? Is it corresponding to 1 million? No. Nowadays it is orders of 10 billion. You know it. So this is orders of 10 to the 10. So if we have just a nanowatt consumption for our transistor, that just explode. If we have a picowatt consumption, still that can introduce some measurable quantity for our power consumption. So simply speaking, nowadays we can build quite a huge system, have tens of billions transistors. Well, that is quite good, but many of them are just waiting for the order by users. So they are, in many cases, they are just in their standby mode. And in this case, important quantity is not their own current, but important quantity is their off current really determines the total power consumption of the entire system. So that's the reason why we are focusing on the expression for this sub-threshold current case. So each of them can be extremely small, we know. However, at the same time, we have extremely large number of transistors. So we have to consider product between these two. So that really makes a big problem. So if we have, for example, 10 times higher I-op current due to certain defect in our process, that immediately increase 10 times higher power consumption in our standby mode. So that is the one we have to understand. So therefore, understanding sub-threshold current is extremely important. Although in our previous lectures we have not spent much time on this sub-threshold current, but practically this is one of the most important one. So now you understand the operation condition. Now our gate voltage is no longer higher than threshold voltage. On the other hand, actually the number of electrons, contributions from electron, this is much lower than this guy. This guy is corresponding to the depletion. So please note that this is just entire square term, and here we have one term from depletion, and here we have a very, very small term from electron contribution. Then in this case, if we have certain expression like square root of 1 plus x, then it can be, when x is quite close to 0, then that can be well approximated as just a linear term, 1 plus a half of this small input argument. So following exactly the same manner, I just make the Taylor expansion. In this case, we can express the total charge, this is a total charge, as a sum of two terms, one term coming from our depletion once again, and another term comes from our electrons. So in our upper equation here, the total charge is obtained from the contribution of these two mechanisms, but it took square root. But when we have a sub-threshold condition where we are allowed it to expand in its Taylor series, then we can decompose the total charge quite clearly into depletion contribution and electron contribution. So this is the one. The point is here we will have many equations, but in my opinion, most important one is to understand this factor. Simply speaking, let me just read this expression. So electron contribution to QS just follows exponential phi s kBT over Q. That is a simple meaning of simple lesson from this expression. So simply speaking, when we can increase our surface potential efficiently, then we can control our electron charge density also quite efficiently. So means that here we have a gate voltage, surface potential, and so how can I say? Let's say the QE, inversion charge or charge contribution due to electron density. So they are connected in this way, and their relation just follows exponential, and this is given as a physical law, but we cannot change this one. This one is internally given. What we can change is we can change the efficiency of a conversion from gate voltage to the surface potential. This one is given as what? Given as our M factor. If this M factor is close to 1, it means that we can efficiently convert our gate voltage change into change of a surface potential. Then that can exponentially change our charge density. That is done here. So simply speaking, here, although we have many terms, but what we can say is now we can clearly identify electron charge density, and drain current is simply given as integrating our inversion charge density with respect to the electron quasi-Fermi potential. So when we do this integration, we can simply say that this one. Once again, there is nothing more here. Starting from its own form for Q sub S, we can clearly identify drain current will follow just the exponential form of this phi sub S, and that can be simply converted into just gate voltage. Delta phi S equal to delta VG. However, we have to have 1 over M factor. If M equal to 1, then yes, we have a quite efficient conversion. And if M equal to 2, 3, 4, then that will give us a quite a poor conversion into our delta phi S. Are you with me? Then please, I think that many of you will eventually be involved with a certain study about a certain kind of a transistor. And when we talk about a transistor, of course, the first thing we have to care is it really conducting or not? So we have to have ID, for example, versus VG. So of course, we have to care about ion. This is quite true. But if you consider an unmatured technology, then please think about also the change of your current with respect to the gate voltage. So what I'm saying is it is quite simple and straightforward. Here now we can introduce m factor as defined in previous case. So simply speaking, now we can say this one. Here we have gate voltage, and when expressed in our gate voltage, it does not have this simple exponential VGS divided by our summer voltage. Unfortunately, it has m factor. So now think about this one. Case 1, m equal to 1. Case 2, m equal to 2. In this case, we will just have exponential kBt over q and gate voltage. That will be the factor. And case 2, when we have m equal to 2, then we will have exponential Vg 2 times kBt over q. And let's say that we have now increased our gate voltage by amount of, for example, just summer voltage. Yes, I just increased 25 millivolt in my gate voltage. Then what will happen if we additionally add one summer voltage? Then now we will say that our ID can be increased by amount of the natural number E. However, if we have m equal to 2, this is the place for our m, then when we add additional summer voltage kBt over q, then that will introduce our ID is just increased by factor of not the natural number E, but we will have just square root of E, natural number E. It means that when we have m value significantly larger than 1, then although we have changes the same amount of gate voltage, the controllability of drain current is much lowered. That is the problem. So simply speaking, now we have the expression for ID. Drain current is simply given as certain factor, but doesn't matter. So here we have an exponential term, and when we take a certain form, so let me just explain a little further. Since in this subthreshold region, drain current is exponentially changing. So maybe you remember that when we talk about on current, we are much interested with 1% decrease or 1% increase in its on current value. However, in the case of off current, actually currently we have no ability to control this subthreshold current, off current, by amount of 1%. This is not the measure of subthreshold current. Instead of that, they are changing exponentially. They can increase 10 times or they can decrease 10 times. So instead of taking this just ID that does not give us correct measure, instead of that we just take the logarithmic function of this ID. This is more relevant quantity, especially when you talk about subthreshold current. So people just takes log 10 of ID. Then what will happen? Here we have a certain free factor, but when we take a log, that is just converted to a certain constant, quite a complicated constant, but that doesn't matter. And here we have an exponential function, and this exponential function will give us this form. If we take the natural logarithmic function, then actually we will have just this input argument. However, unfortunately, we love to use this logarithmic function with its base 10, log 10. So that's the reason why, unfortunately, here we have a certain factor due to coming from difference of a base. So instead of a natural number, we use just digit number 10. So yes, please understand this complication. And after that, we take change of this log 10 ID with respect to the gate voltage. So that is the point many students face some difficulties. So why we have to care about this quantity? Why we don't consider this kind of VGS quantity? Yes, this quantity really depends on the magnitude of ID. Let's say if we have 1 nano M case and 1 micro M case, and let's say also we have the same 10% difference. If we have 10% difference, then that would be 0.1 micro M. Also this one will be 0.1 nano M. Although they are all sharing the fluctuation of 10%, but actual amount of change are huge difference. So what we wanted to say is, in this case, in this especially sub-threshold current case, we are not interested with this delta value itself, but we wanted to concentrate on the ratio of change. So that's the reason why instead of taking this ID itself, we first takes the log 10 and measure its sensitivity with respect to the gate voltage. So then when we do it, the result is quite obvious. This constant goes away because we take the derivative, and when it takes the derivative with respect to the gate voltage, yes, this term also goes away, and here we have quite a simple expression for our value. Just 1 over summer voltage and 1 over M, and here we have a constant. And when we take its inverse, so usually yes, this one is not written in its original form, just invert it, 1 over this factor, and this one is called as sub-threshold slope. This concept is extremely important, and you should be able to derive this kind of behavior, and eventually you have this form. Yes, since we take the inverse, so its inverse is also seen here. This is about a certain number, 2.3. So combining the entire term except for this M value, kVt over Q, thermal voltage, and log 10 at 300 Kelvin, we have a really well-known famous number for this quantity. Thermal voltage in this case is 2585 millivolt, and when we multiply log 10, then happen to be, this is just an incidence, we have 60 millivolt for this case. So simply speaking, our sub-threshold slope at 300 Kelvin is given as 60 millivolt per decade only when M equal to 1. When we have the ideal case, we can have 60 millivolt per decade. Once again, let me just read this statement. It means that in order to increase our drain current 10 times, we need 60 millivolt more in our gate voltage. If we apply 60 millivolt to our gate voltage additionally, then we will get 10 times higher current. This is the meaning of this expression. Once again, this is the ideal case, and if we have M equal to 2 cases, then what will happen? If we have 60 millivolt additional voltage in our gate voltage, we will have not 10 times higher current. We will just have square root of 10 times higher current. It is just corresponding to 3, lower than 4. So simply speaking, if we have a good transistor, then by changing 60 millivolts in our gate voltage, we can have 10 times higher current. But if we have a bad transistor, although we have increased our gate voltage, same amount of voltage, 60 millivolt, our current increase is quite marginal. So let me just once again draw now ID versus VG curve. Here we have ID and here we have VG. It simply means that, let's say that at a certain point, a transistor shows a certain drain current. And if this transistor is ideal, M equal to 1, in this case, when we increase our gate voltage by amount of 60 millivolts, say that VG plus 0.06 volt, this is corresponding to 60 millivolt, then we will have 10 times higher current. So where can we write down? Please note that this we are drawing it in it's a semi-logarithmic graph, and now we will have this form by introducing just 60 millivolt increase, then we will have 10 times higher current. Let's just do it further. For example, if I just do it 5 times, then how does it look like? If I just step 60, 60, 60 5 times, then we will have just VG plus 0.3 volt. If we change just 0.3 volt in our applied gate voltage, if that is the true, then we will have 100,000 times higher current than our initial ID value. So simply speaking, by changing 0.3 volt, we can drastically change our VD values 5 orders of magnitude. That is the consequence of this expression. So, for example, let's have a look at certain one. Here we have 0 gate volt, and these right branches are corresponding to our N MOSFET, and you can see that here the value is more or less corresponding to a certain value here. And where can you find the 0.3? Yes, 0.3. And let's go to this way. Then you can see certain number. So sorry about that. So sorry about my ugly drawing. So also that's not perfectly vertical and perfectly horizontal, but you can do it much better than me. And when you can, what you can see is here and there we have change of 0.3 volt, and change in your current is about 4 orders of magnitude difference is involved. So even in this realistic case, so this is not far away from our state of the art. This was published in our 2 years ago, 1.5 years ago IDM conference. So the best conference for electronic devices, and this is from Intel, and they showing that when we change the gate voltage by 0.3 volt, we can modulate our drain current by orders of 4 orders of magnitude. Of course, if it is really the ideal case, we expect 5 orders of magnitude. And where can you find this degradation? Actually, this slope itself is really ideal. It is really corresponding to 60 millivolt per decade. And here we have degradation in its slope, and this is because we are already entering into the threshold voltage. So you know that when you measure your sub-threshold slope, then that is the current state of the art device is quite close to its ideal value, 60 millivolt per decade. So please try to measure it. This slope is corresponding to your sub-threshold slope. Then I can challenge you by asking some questions. So let's say that this is S. Then which device is a better device? For example, this device or almost vertical device. This one and this one. You know, this one shows much better behavior, and this one is quite poor behavior. Although we change our gate voltage, current is not effectively modulated. So this guy is a bad guy, and this guy is a wonderful one, but it does not exist in reality, because this one is the best one we can expect from physical law. We cannot disobey the physical law, and steeper than 60 millivolt per decade cannot be allowed due to physical law. So this is not accessible. Then my question is, so now you know that more vertical, more better, but question is, then what is the value of S value? Is it corresponding to 60 or 120 millivolt per decade? Millivolt per decade. If we have a bad guy, then it has the value corresponding to much higher than 60. Okay, so minimum value of S is 60, and when we degrade our transistor, actually this value increased, because you know here we have the leading factor M in our S expression. So this value is extremely important. So nowadays the value quite close to 60 millivolt or within the values like 60 and 70 is regarded as the normal value for our state-of-the-art device. But please note that the current graph we are currently looking at is obtained from the state-of-the-art devices. It means that we have introduced multi-gate architecture in this graph, and when we come back to our planar MOSFET, so the MOSFET that has a single gate and p-type substrate, in this case, in our planar case, this sub-threshold slope cannot be like 60 or 70. The reasonable value in the previous case was about 90 or 100 millivolt per decade at the time. So maybe you, since we are now currently living in 2026, maybe you can ask me how our ancestors can live with that poor transistors. But please note that before introducing multi-terminal, multi-gate structures, that was the best thing we can have, because what is the expression for M? M is equal to 1 plus C aux over C depletion capacitance. And if we cannot kick out our depletion capacitance at all, then we should have value much higher than number 1. So previously we had the values, the ratio, well-known ratio about 0.3 or 0.4. That was an acceptable range of our value. And let's say that if M equal to 1.3, then you will have 78. And when you have 1.4, then you will have 84. That was the thing we could have at best. So 1.3, 1.4, that was regarded as a good or reasonable value. And our sub-threshold slope was, if that is lower than 100, so people thought that, okay, it's acceptable, but we wanted to improve it. So that was the case. But nowadays, no longer we are using planar MOSFET, and now we have introduced multi-gate transistors. And the peculiar point of these technologies is it doesn't have C depletion. Actually, there is no C depletion. CDM in our expression is exactly almost close to 0. So that's the reason why now in this multi-terminal device, M factor is almost close to 1 once again. So we were able to get really ideal, almost ideal 60 millivolt per decade for our case. Is it really good or not? That is tremendously important. If we are currently using still planar MOSFET, then we cannot reduce our VDD value. Starting from this one, starting from certain I off level, we wanted to arrive at certain on current level. Our desire is quite clear. We always wanted to maximize this on current. We wanted to increase it, ever increase. The desire is ever increase, but we don't want to have this kind of thing. Well, it's quite easy to say this way, or quite easy to this way. If we allow ever increasing off current, then it is also quite easy to have much higher drain on current. But this is not acceptable. Who decided this value? Who decided this value? The static standby power consumption just requires us to maintain off current level in a reasonable way. So more or less this off current is fixed, and let's say once again we have quite a poor device whose S value, sub-threshold slope, is not ideally 60, but let's say that 90. Then what will happen? In this case, if we go to 0.1.5 volt, 0.15 volt, we can expect in this case 2.5 orders of magnitude increase, 2.5 have, we can expect certain increase. Oh, sorry. We can expect certain amount of increase in this case, 2.5. Then in our case, in our 90 millivolt per decade, our expected increase is much lower, and it is almost close to just to 1 orders of magnitude increase. So simply speaking, we will just reduce its slope twice. So just to push this behavior. Now it is going in this way, and it is now going in this way. And how long should we wait? Yes, that will be the behavior of our transistor when we have much worse sub-threshold slope. In order to arrive at certain amount of ion value required for certain technology specification, we have to spend much wider gate voltage span. It means that VDD value should be increased, and when you increase your VDD value, it automatically increases your power consumption. Your static power consumption is increased. Your active power consumption is also increased. So this is not acceptable. So simply speaking, planar MOSFET cannot match the current performance level of our multi-gate transistor, only because they have this M factor much higher than 1. And this is originated from the increase or existence of depletion capacitance. In order to change our surface potential, also we have to consider our depletion cap. That is the critical point. However, when we go to the multi-gate case, we can eliminate this one. Then maybe some of you guys can ask me this question: what is the exact relationship between this multi-gate architecture and non-existence of CDM? Why we don't have a depletion cap when we introduce multi-gate system? So can we have, for example, can we have also CDM equal to 0 even with planar MOSFET? How about this one? What is the relation between these two ones? Actually, the answer is yes, we can make CDM equal to 1 even when we have planar MOSFET. I mean that not exactly planar MOSFET, but single gate structure. With single gate structure, we were able to get this CDM equal to 0. The trick was quite simple. Trick was, now let's say that this is silicon, and here we introduce very thick or sometimes very thin oxide layer, and the thickness of this silicon layer is typically orders of 10 nanometer. I mean that not exactly 10, it is about 50 nanometer or something. And now we have relatively thin layer of silicon layer, and in beneath of that we have oxide layer. And beyond this one, just to build a transistor, once again gate, and here we have a gate oxide and source and drain. Yes, this kind of a planar MOSFET without having the substrate contact can be actually fabricated. Then question is, what will be the CDM value of this structure? The answer is, in this case, CDM equal to 0. Please note that what is the meaning of our CDM? CDM in this case, not here, CDM is corresponding to the maximum value. So depletion cap. How do we have a depletion cap? In our case, when we place our transistor in its subthreshold region, when we change our gate voltage, we have an increase of depletion layer. That is corresponding to the CDM. But in this case, in this technology called as SOI device, silicon on insulator technology, already this relatively thin silicon body is depleted. So there is no further place to be depleted. Actually, there is no hole at all already. In this case, if we apply additional gate voltage, but there is no further neutral reason to react this potential change. So in this case, CD is really equal to 0. So then natural question is, then if that is true, then in this SOI device, can you expect 60 millivolt per decade slope, substrate hole slope? The answer is yes. We had also quite an ideal subthreshold slope. So in its performance term, it shows much better than our previous planar MOSFET. So who support this technology? You know, maybe you have heard about a company called as IBM. So IBM was the king of this SOI technology. They strongly supported this technology because performance shows much better. But unfortunately, at the time, generating this kind of SOI structure, very thin silicon on oxide layer and once again silicon, that is related with expensive wafer. From its starting point, wafer itself is much more expensive than just silicon wafer. So cost effectiveness is the big trouble in this technology. Okay, so once again, let me just come back. So everybody, even when we before introducing this multi-gate structure, people understood that subthreshold slope is the key factor, and they try to reduce it as much as possible, but that was limited by the factor M, which is closely related with depletion capacitance. But nowadays, with multi-gate structure, now we can realize this fully depleted substrate. So we effectively kick out this CDM factor from its M value, and now we can say that M is quite close to number 1, ideal 1. So simply speaking, please remember, in our multi-gate transistor, in its subthreshold region, when you change your gate voltage, then it is directly converted into the change of your surface potential. That is quite a significant factor you have to remember. So I guess that's all for my today's lecture. Once again, this is so important. So and also my final comment on this stuff is, people felt that this is the limitation, and limitation enforced by natural law. Why we have to suffer from this 60 millivolt per decade? If we can overcome this barrier, 60 millivolt per decade, we can enjoy quite a lot. So they dreamed. What they dreamed was happen to be I coined a bright idea. So my transistor can have, for example, 30 millivolt per decade reliably. Then they thought that, okay, my transistor's IV characteristics no longer governed by this hard limit. So say that twice rapidly I can increase my current. So by arriving at this point quite quickly, then we can arrive in this way. Then they thought that, okay, by doing so, we can significantly reduce the operational voltage VDD. Then it gives us tremendous reduction of power consumption. That was their dream. So, in almost more than 2 decades, people have tried to find out a technology to support this kind of much steeper transistors. So I wanted to ask you or recommend you just to make a search in internet, steep slope transistors. If you search in this keyword, then you will find so many attempts to build this very dream technology. If it is really available, then we can reduce our operational voltage quite a lot. So that can drastically reduce the power consumption. So everybody will be really happy. So, but as of 2026, unfortunately, there is no technology currently in mass production. So still there are ongoing research, but this is a little bit difficult to be used in mass production, because mass production really requires the reliability, the really working technology. Not in a lab, but in a fab, you should be able to make quite well-behaving technology. So that's one thing. And the final comment is that we have a few more slides, but this is just showing that our threshold voltage here, simply speaking, our threshold voltage really depends on the back bias dependence. So up to now, we have assumed that if source is the reference, then we always thought that also body or substrate, they are also grounded. That was our previous assumption. However, this equation 5.59 just says that if we introduce non-zero body bias BB, then we can actually control threshold voltage. But please note that here we have a negative sign here. Question is, if we wanted to increase threshold voltage, what should do is not increase our body voltage. If we increase body voltage, then it can actually reduce threshold voltage. In order to increase threshold voltage, actually we have to apply negative value for our p-type substrate. It means that now, let me just say, instead of 0 ground, we apply -1 volt. Then if we introduce -1 volt to our substrate, then threshold voltage can be increased. So go to this one here. When we increase the absolute value of a negative bias voltage, body voltage, then we can increase threshold voltage. So, for example, starting from this 1 volt, if we apply minus 2 volt to our substrate, then we can increase our threshold voltage quite a lot. Why we have to care about this seemingly unimportant factor? Because sometimes when transistor is turned off, we wanted to intentionally increase its threshold voltage. If its threshold voltage is intentionally increased, then we can further reduce I off value. So when certain block is completely turned off, then we can intentionally increase all of them or their entire sub-threshold voltage quite a lot and drastically suppress the power consumption by that block. That was a technology actually being used by certain circuit. Although we are currently living in an era of a gate-all-around transistor and FinFET, but nobody, not everybody is using FinFET and gate-all-around transistor. There are many people actually using planar transistors in their circuit design, and they are actively using this technique to reduce power consumption. Okay, thank you, and see you.